Okay. Connecting. And how do I know it's recording? Oh, it is recording. Stop, pause recording, stop recording, resume recording. Okay. Okay. Looks like it's recording. I'm hoping and praying it's recording, because sometimes even if I record, the sound doesn't get recorded. And then, oh gosh, what a waste of effort. Okay. 6.2, we're looking at adding and subtracting vectors. So last time we did introduction to vectors. What's a vector? A vector is just an arrow, head to tail. The head of the arrow points to the end of if you have 2 points, let's say A and B, then the tail of the arrow starts at A and ends at B. Okay, and we represented vectors either through writing that or as a single letter, like U or letter V. And so today we're looking at how to add two vectors. Okay, so there's a couple of ways to add two vectors, and one is called the triangle law of vector addition. So to find the sum of two vectors labeled U and V, okay, and remember vectors always have this arrow above the letter that signifies it's a vector. And a vector, the difference between a vector and a scalar, is that vector has a direction and magnitude, whereas a scalar is just a number, an expression, a variable. Okay, so we're dealing with something with both magnitude and direction. Then if I have two of these vectors, I can add them together in this fashion. So when we add two vectors, we take the first vector. Let's say the first vector here is vector V. Okay, and I take the second vector, vector U. You connect the vectors head to tail. So the head of the first vector is attached to the tail of the second vector. Okay, and then I draw something called the resultant vector. The resultant. So when I say 1 + 2 equals some answer, where I say the answer, I'm going to say the word resultant. Okay, so when you're adding two vectors, it's called the resultant. So the resultant vector is drawn from the tail of the first vector, the vector V over here, to the head of the second vector, the vector U over here. And then I can say that's V plus U, or I could just use the letter R to represent the resultant. Okay. But remember, addition, just like when we're dealing with scalars, if I wrote 1 + 5, that's the same thing as saying 5 + 1. They both give you the same answer. When it comes to vectors, it's the same thing. I could write vector U first as the first vector. So vector U, and then vector V can come second. And I just have to make sure I connect them head to tail. So the head of U connects to the tail of V. And then I can draw my resultant vector from the tail of U to the head of V. Okay. And yeah, so that's going to be U plus V, which is still my resultant vector. And they are the same vectors. If you imagine I superimposed this one on the left, this orange vector on the left with the one on the right, they are the same vector, the same orientation, the same magnitude, same direction. Okay. And then if I combine these two triangles that are created from these two vector diagrams, we call this a vector diagram. Okay. If I can combine those two triangles, I can create this diagram that I have here at the bottom called a parallelogram. Okay, it's called the parallelogram here, which is a different way of adding two vectors. Okay, so instead of doing the way I was just showing you, I could also take vectors U and V and place them tail to tail. So again, the tails of each vector are connected by their tails. And then I can draw a parallelogram out of that, right? So, the vector V, it's draw a parallel dotted vector over this side. And for vector U, I just draw a parallel dotted vector up over here. And I just create a parallelogram. And the diagonal of that parallelogram would be the resultant addition U plus V. Okay, so that's called the parallelogram law. And the first one's called the triangle law. Okay, the triangle law is what we are going to be using most often. So use most often. So I'm going to, in all of my examples, like 99% of the examples, I'm going to be using this triangle law of adding vectors and not so much the parallelogram law. Okay. All right. Moving on to the next page here. So again, just highlighting the parallelogram law. What's that law state? So finding two vectors when they are drawn tail to tail, you create a parallelogram, and then you can find the diagonal of that parallelogram as your resultant. Okay, now just to show you a vector addition, your vectors can be oriented in all sorts of different ways, and they can be located in all sorts of points in a 3D space or a 2D space. So what I'm going to do is here show you how to add three vectors and create a vector diagram. I'm just going to trace over these vectors with each of a different color, because I just want to show you that how these work. So if I have three vectors A, B, and C shown like this, there's no magnitude values, no angles or anything like that yet, just a plain arrow, okay? And you can see the arrows are all different sizes, right? And that means something, and that means that they have different magnitudes, okay, different sizes, different magnitudes, and they all point in different directions. But I'm going to be looking at these particular sums. So I'm going to look at the first one, A plus B. And when you're dealing with vectors, yeah, you can take each vector. Here's vector A and here's vector B, and I can put them together, okay? And I can connect them. I'm going to use the triangle law, and I'm going to connect them head to tail. So the head of the first vector is going to connect to the head of the second vector, okay? Or if I wanted to, I can take the vector B and I can add it to vector A like so down here, okay? But I'll follow the expression given, A plus B. So I'll write it as A first and then B, okay? And so here I'll label vector A and vector B. So when you're trying to duplicate this in your notes, just try your best to get the correct size of the arrow. It may not be it might not be exact, but you know, just try to approximate the size of the arrow and the way it's oriented at that angle. Okay. And then you take a ruler, and so for most things in this chapter, you should have a ruler or some kind of straight edge plastic card or something to help you draw these diagrams, because pretty much every problem we're going to deal with, we're going to draw some diagrams. So in this red color, I'm drawing the resultant vector. So when I add A plus B, the resultant is connected from the tail of A to the head of B, and that's called vector R, or I could say that's A plus B. A plus B equals vector R, resultant. Okay. Okay, so that was the first one. The second one, oh, just to illustrate one more thing, I'm going to just copy everything here, and I'm just going to just paste this here just to show you. Let's cut that away. Just to show you one thing. So if I added it the other way, so if I did B plus A, okay, the resultant should be the same vector, right? I can take this resultant. Oh, maybe I gotta just do it one piece at a time. I could take this resultant and it should fit, right? If I just shift it down here, it should fit like that. So the resultant is still the same no matter which way I add the vectors, A plus B or B plus A. Okay. Looking at the second one, A plus B plus C. Okay, so we already calculated A plus B. So I'm just going to copy that vector down here. Okay, so there's vector A plus B. And I'm going to add that now to vector C. So I already have vector C up here. I'm just going to bring it down. So connected head to tail when you're adding vectors like so. So the head of my first vector connects to the tail of the second one. And then I draw the resultant. So drawing the resultant is from the tail of the first vector to the head of the second one. Like so. And that would be A plus B plus C. Or I can call that R, my new resultants for this example. Okay, notice, so my vectors head to tail when I add them, but when I find the resultant, it's tail to tail, head to head. Okay, do not draw the resultant the other way. Like, do not do a head to tail, head to tail, head to tail. It has to be the tail of the first vector to the head of the second one, and you draw the arrowhead for the resultant there at the second one. Okay. Maybe I should make a little note of that. So for the resultant, connects from tail of the first vector to the head of the second vector. Okay. And then for the third example, we have, what does it say there? It says A plus B plus, oh, sorry, then B plus C is the next one. So I'm going to add B and C. So I'm just going to do a little bit of a copy paste. So B and C. Okay, so again, these vectors can be anywhere in 2D or 3D space, but you can take one vector and bring it over and connect it to another vector. So here's B plus C connected head to tail. Okay, and then I'm going to draw a resultant. And so I'm going to go from the tail of B to the head of C. So vector B plus vector C. Okay. Now, and then the final one, the final example there is B plus C in brackets. Oh, A plus B plus C. Okay, so A plus B plus C. So I'm going to add a vector A into all of this. I'm just going to find a copy of vector A, and we're just going to copy that, paste. Okay. And I could take the resultant from the previous example, but I just want to show you one where I put 3 vectors on the same diagram. So A plus B plus C, like that. Okay, and here, remember, even now if you're adding 3 vectors together, you still connect them head to tail, head to tail, head to tail. So the head of A connects to the tail of B, head of B connects to the tail of C. Okay, it's the resultant that does not follow that same logic, right? You have to connect the tail of the first vector to the head of the last vector to draw the resultant. So here's the resultant. A plus B plus C. Okay. Okay, I will leave the you try question for you to try later on after I finish recording the video. For those who just came in late, I'm recording on Zoom for those who are not here. And all of you, of course, can have the copy as well. So, any question on that so far? All right, let's look at the next page. Opposite vectors. So if you have a vector A, its opposite So if I look at this diagram, vector A, and I have negative A, okay, these are opposite vectors, right? So when I do a negative, so here's a vector. If I make this vector A negative, all I'm really doing is changing the direction. So it goes from pointing upward, now it's pointing down and to the left. It's changed the arrowhead's direction. That's all the negative signifies, okay? Now, if I were to add these two vectors, the thing about opposite vectors is that they don't make a triangle, right? I don't get a little triangle law action going on here. It's just going one way and then back down, up, then back down. So wherever you start is also where you end, okay? So there is like zero change, but I wouldn't say zero is the answer, right? When I add vector A plus negative A, is not zero, it's actually called the zero vector. So when I add A plus negative A, if it was algebra, you know, A minus A is zero, but with vectors, it's going to be A minus A is zero, the zero vector. Okay, and so the zero vector is still a vector. It's by definition, or kind of arbitrary, so to speak, we say it's a zero vector. Okay, there's no specified direction, no length, but it's still called a vector. Okay, this is how it has to be, and by definition. Okay, so that's that. We're also going to look at angles between two vectors. Okay, so we have a lot of trigonometry involved when we study vectors in chapter 6 and chapter 7. Okay, so we're going to bring back this idea of theta, theta being the angle between two vectors formed by joining the vectors tail to tail. Okay, so I have a vector u and a vector v here, and the theta between them is just an angle given tail to tail. So why is this important when we do some problem solving? Maybe we're going to say, hey, you have a 5-kilometer vector and an 8-kilometer vector acting 60 degrees to each other. Okay, so if I don't give you a diagram, the diagram you have to imagine in your mind is I have two vectors and the angle 60 degrees to each other is the angle between them tail to tail. Okay, it also applies to think in some books it might say head to head is your angle, which is the same thing. Okay, so that's still the same thing. And the reason why that's the same thing is because if I extended these vectors backwards, okay, and just drew heads like that, then opposite angle theorem says, well, that theta is going to be this theta. Okay, so your vectors could be joined head to head, and that's the angle between them, or they could be joined tail to tail, and that's the angle between them. Same thing. Okay, but for most things that I'm going to give you, pretty much everything as much as possible, it will be tail to tail. All right, so let's do an example, because we're going to just jump right into the physics type problems. And so again, warning, a lot of vectors problems are physics problems. So if there's something about the physics you don't understand, even during a quiz or a test, you can ask, and I'll help you out a little bit. Okay. So a boat with forward velocity. So again, velocity is that kind of analogous to speed, but now velocity, the difference between velocity and speed is velocity has a direction, okay? Whereas speed is just a magnitude. 14 meters per second is the speed, but when I say 14 meters per second going north, that's a velocity. So I can create a vector out of that. So you have a boat going that velocity traveling across the river with the current or the speed of the river, moving at 5 meters per second toward the east. Find the resultant velocity of the boat. So this new term here, resultant velocity, just says find the resultant vector. Find the resultant vector. Okay. So the first step in doing any of these problems when you're adding two vectors is draw a vector diagram. Okay, so I have to create vectors out of these different parts of the example. So I have a boat going north. So I'm going to draw an arrow pointing north. Let me switch back to black ink here. So here's a vector going north. 14 meters per second. And I'm going to draw a vector for the river going east, 5 meters per second. Okay, and if you forget your compass, you can quickly draw one north, south, west, east. Back when I was in high school, I mean, there's different ways you can learn to memorize where north, south, east, west was, but I always thought about, oh, Dundas West Station is on the west, and then that means the opposite is east. And then I always remember north and south. So, okay, that sort of might help you, or if you have other ways to remember that, then that's the way. Okay, and so here's a diagram of the situation. I have a boat here going upwards, 14 meters per second, and the river is acting on the boat going east, 5 meters per second. But if I'm going to use the triangle law and create a proper vector diagram, I'm going to take these two vectors and connect them head to tail. Okay, so what I'm going to do is just recreate this diagram here on the side and move the 5 meters per second vector up here. So now I can connect them head to tail. Okay, so you might want to think about the first diagram being more of like, here's the situation. And the right diagram on the right, this is going to be my proper vector diagram, connected head to tail. And I'm going to create the resultant vector by connecting the tail of the first vector to the head of the second. Okay. And I will label that R. If you've been taking physics and you're more familiar with by writing this as velocity V and maybe using a subscript R for resultant or G for ground velocity, I'm okay if you do that. Okay, I will recognize that because I've done physics and I'll know all that. But in my examples, I'm going to show you. I'm just going to stick to just using R as the resultant. Okay. So let's find the resultant now. Okay, so there is going to be a magnitude and a direction. I need to find magnitude. Let's start with the magnitude. Yeah, we're also going to look for direction. Find the magnitude of the resultant. So I'm going to use absolute value signs around the R to show that I'm looking for a magnitude. Okay. And if I look at this diagram, I should see that, hey, I have a triangle. It's a right angle triangle because I know north and east are perpendicular to each other. So that's going to be a 90-degree angle there. And if I have a right angle triangle, I can think of what in my math toolkit do I know to solve a right angle triangle? Yeah, Pythagorean theorem. Good. It's it's been done over and over and over again since grade 8, grade 9, and so we'll use that. So my resultant squared is equal to 14 squared plus 5 squared. Okay, so the hypotenuse squared is equal to the sum of the squares of the other two sides. So then you take out a calculator. 14 squared plus 5 squared, oops, is 221. Okay, and then remember that's the resultant squared, the hypotenuse squared. If I want just the resultant's magnitude, I have to take the square root of 221. And that's going to be 14. I'm going to round it to 14.9 meters per second. And I'm just going to, just one decimal place is fine for this example. The question is, how do I know how many decimal places to round? If you're familiar with significant digits, significant figures, then you can use those rules. If you're not, then I would suggest look at the problem. If they use 1 or 2 decimal places, then you're using 1 or 2 decimal places for your final answer. Otherwise, 1 decimal place is good enough for me. Okay. Let's look at, so that's our magnitude. Okay, so the boat, if the boat's engine is pushing at 14 this way and 5, and the river is pushing at 5 toward the east, the actual velocity of the boat, according to some observer on the shore, would be 14.9 meters per second in this direction. But what's that direction? I got to find that too. Okay. So I'm going to put a little angle theta there inside my vector diagram. And I'm always drawing theta at the tail of the resultant. Okay, so step 3, find the direction of the resultant. Okay, and I'm going to theta at the tail of R. Now there might be some times where theta is difficult to put it at the tail of R, but most of the time you can. So theta, back to the diagram up here. It's not Pythagorean theorem we're going to use. We have to use one of our trig ratios. Okay. If I'm given the opposite side of the angle and I'm given the adjacent side of the angle, opposite over adjacent, recall SOHCAHTOA, tangent ratio. Tangent is the opposite over the adjacent side, so that's the ratio I'm going to use. Okay, so tan theta equals the opposite side over the adjacent side. And so the tangent of theta equals 5 over 14. 5 over 14. And if I want angle theta, remember, solving for an angle means you have to use the inverse of the ratio. So the inverse tangent of 5 over 14 is 19.6. So I'll round that to 19.7 degrees. Okay. And remember, it will not always be tangent theta. It could be sine theta or cosine theta, depending on the diagram that you draw, the problem that you're doing. Okay. And so now I have my 19.7 degree angle. My final statement, I'm going to say here the resultant velocity of the boat is 14.9 meters per second. Okay, and here's the important part, the direction. You just can't write 19.7 degrees. You have to give me some either a quadrant bearing or a relative angle. Okay, and if the question is giving you north and east as part of the given vectors, then you have to use a quadrant bearing or a quadrant angle. So if I'm looking at this, imagine a compass, north, south, east, west. That angle theta is going to be north theta degrees swinging north to theta degrees swinging toward the east. So I'm going to say north 19.7 degrees east. North 19.7 degrees east. Okay. If we were not working with north, south, east, west, then you would say, oh, then it's going to be the resultant is 14.9 meters per second, 19.7 degrees relative to the 14 meter per second velocity. So it's relative to one of the vectors that's given. Or sorry, 19.7 degrees. Okay, again, I'm going to leave the U-try example for later. I just want to continue with the video lesson here. Subtracting vectors. There's a whole lot of note here for what I'm just going to simplify as something very simple. When subtracting vectors, let's write this down, please. When subtracting vectors, add the opposite. Add the opposite. Add the opposite. Okay. What does that mean? I can use a diagram below to show you. I'm going to just highlight vector A. And I'm gonna also trace over vector B. Okay, so for example, if I had vector A take away vector B, okay, vector A take away vector B, when I say add the opposite, what that means is you keep the first vector, vector A, and you add the opposite of B, which would just be negative B. Okay. If you think about algebraically, it's just like, oh, you're always taught when I do A plus negative a number, then I should just write A minus that number. Okay, but with vectors, I'm sort of going in reverse. A minus B equals A plus negative vector B. Why am I doing that? Because I'm going to take vector B, this vector right here, and flip it around. Oops, that's not how I wanted to do it. Gotta rotate it twice. Okay, rotate and rotate one more time. Okay, so you changed B's direction. So this is now negative B. Just gonna put it down here. Okay. Well, I didn't have to actually do that. Okay, well, if you're drawing it, you could draw it there, or I could just, well, that's fine. We'll just leave it like that. Now, if I connect the resultant from the tail of A to the head of negative B, this resultant, that's A minus B. Okay, and it's already been drawn in the diagram up here, but just to show you the complete parallelogram law, it should match, right? So if I move that vector up to the top, it should match what I have up here. Well, pretty close. Okay. Okay, so that's A minus B. So just remember, when you're subtracting vectors, you add, instead you change the sign to add, and then you add the opposite vector. A does not change. A is still A. It's the second vector that changes. If you're adding more than two vectors, so three vectors, or sorry, if you're subtracting more than two vectors or three vectors or four vectors, same thing. You keep the first vector the same, you add the opposites for the rest of them, whichever ones you're subtracting. Okay. So down here as an example, expressed as a single vector, vector C to D minus C to B. So when you're dealing with points, you're connecting vector C to D. So the tail at C and the head at D. Just draw a vector head like that. And C to B is another vector here. So here's the vector connecting from C to B. So the tail of C to the head of B. So that's why order is important. When you read C on the left, D on the right, and C on the left and B on the right, that's the order in which we connect those points and draw the arrowhead. But if we are subtracting, we have to make that change. So C to D plus the negative of C to B. The negative of C to B is taking this vector here and rotating or changing, flipping the direction, opposite direction. So I'm just going to rotate it around. Now it's changed direction, and conveniently it is connected head to tail with the other vector. So when I draw my resultant, I'm just going to draw the resultant from the tail of this one to the head of the other one. Okay, and I'm allowed to do that because remember, addition is commutative. I could write, so negative C to B is just like saying I'm now drawing the vector connecting B to C. Okay, and I'm adding C to D with that. That doesn't change. Okay, and I can switch them around. I could say B to C plus C to D, because addition is commutative, right? 5 plus 1 is the same as 1 plus 5. And then the resultant I have in red, which is the vector from B to D. Okay. And if you set up the equation just right, you'll notice that the inside letters are the same. So BC and CD, C is the inside letter. Those will just cancel out, leaving you with B to D. Okay, it's another little trick that you could use is that if you line them up such a way that they are the inside letters are the same, then you can make those cancellations. But don't depend on that. Just stick to the diagram and you'll be fine all the time. Okay, the next one, A to C minus D to C. A to C, I'm going to draw here. Actually, let me erase the other one so I don't clutter them. A to C is the vector connecting point A to point C. And vector D to C is the vector connecting point D to point C. Okay, notice how they're connected head to head, but it's a subtraction. So I still have to change that to an addition, right? So A to C plus the negative of D to C. Always change it to an addition. I got to reverse the direction of D to C now. So I'm going to rotate that around 180 degrees. Oh, I should have just, let's just redraw the arrowhead. Okay, so there you go. And I can now rewrite this as A to C plus C to D. Okay, so the negative of the vector connecting point D to C is just equal to the vector connecting C to D. Okay, and then the resultant, if I draw the resultant here, just double check everything's connected head to tail. Then I can now draw the resultant from tail of the first vector to the head, the second vector. And that's vector A to D. Okay. All right, let's do one more. One more problem on the next page. Another vector diagram question where you have to solve a problem. So the magnitude and direction of the sum of two vectors, u and v, just like the example before. I have their magnitudes as 5 and 8, respectively. So 5 is the magnitude for u, and 8 is the magnitude for v. And the angle between them is 30 degrees. Okay, so I have the vectors drawn here with a parallelogram law diagram, or you can draw them as a triangular law diagram. So I'm going to do it as a triangular law. And so when you draw it using the triangle law, you have to connect them head to tail. So here's vector u is 5 units, and vector v is 8 units. So they are connected head to tail. Now remember, the angle is not going to be 30 degrees when you draw that diagram. Okay, so when they are tail to tail, it's 30 degrees. But that 30 degrees, when I translate that vector over, that 30 degrees is over here. Okay, but I don't need that 30 degrees. I want the angle inside the triangle because we're dealing with solving triangles here. So the angle inside the triangle is going to be 180 minus 30, which is 150. And that's just the complementary or supplementary angle rule. All right, so we have a flat horizontal line, the angle adds up to 180. Then the resultant is drawn connecting the tail from 8 to the head of 5. And then you can label that R, or since we're going to be finding the magnitudes, it's going to be the magnitude of R. Okay, but in this diagram, they use U plus V. That's fine too, okay? Now, the difference between this problem and the one we did two problems ago, we had a right angle triangle. This one's not a right angle triangle anymore. Okay, we have to solve this triangle. We have two sides given. We have the 8 and the 5 and the angle between them. There is a trigonometry law that we can use to solve this. If you remember, Kiara, cosine law. Perfect. So step 1, diagram. It's going to remind us of steps again. Step 2, find the magnitude using the cosine law. Okay, Cosine law because it's the side, two sides and the angle between them, SAS. It's an SAS triangle. You also use a cosine law if you have three sides given and you have to find the angle. Okay, but in this case, it's just two sides and the angle between. Do you guys remember the cosine law? No. Okay, here's the cosine law. Ishwar, okay, go ahead.
C squared equals cosine A. Okay, I already failed, did I? You know what, never mind.
Think of Pythagorean theorem. It's very similar to the Pythagorean theorem. Then the adjustment, yeah, cosine C, there you go. So it's like Pythagorean theorem, but then you have this adjustment to take care of the angle because it's not 90 degrees. Remember, if it was 90 degrees, cosine of 90 would be 0. And then this term disappears. And that's how you have Pythagorean theorem. Okay. Now, I'm going to tell you something. You got to know the formula. Okay. You got to memorize the formula. With enough practice, you'll know it. Okay. But if you don't remember it, start memorizing this as well as the sine law now, because the other regular calculus section, they don't get the formulas and they have to memorize it too. So that's the cosine law, okay, where C is the side you're solving for, opposite to the angle you're given. So we were given the 150. So C squared ends up being the resultant squared. And that's equal to the sum of the squares of the other two sides. So it's 8 squared plus 5 squared minus 2 times 8 times 5 times cosine of the angle between them, 150. Oh yeah, one question that has come up in the past. Well, sir, this is vectors, right? Cosine law is like a scalar formula. Does it really apply? And the answer is yes. You just adjust the cosine law formula, if I can write it here on the side. It's just like the magnitudes of the vectors, right? The cosine law formula should look like this when you're dealing with vectors. So minus 2 times the magnitude of vector A times the magnitude of vector B times the cosine of C. So in some textbooks, that's what they'll do. Just put some absolute value signs and then turn every letter into a vector. Okay. Now that's if you don't do that, then I'm not super concerned that you write out the cosine law like that. What I just want to see is, hey, you can do this calculation over here. Okay. At the end of the day, it's still a triangle and you're still solving a triangle. Now solving for R, make sure you, if you have a calculator with you, do it right now, because I want to make sure you still remember how to calculate this properly using the correct order of operations. And if you calculate it, your answer should be, well, for R squared, about 158.3 if I round it to 1 decimal. Okay. If you don't get 158.3, make sure you are doing the 2 times 8 times 5 times cosine 150 together. That's usually the common mistake where students do 8 squared plus 5 squared minus 2 times 8 times 5, and then they multiply by cosine 150. So be careful. Order of operations really is important. Okay, if I take the square root of that, I get 12.6 units. So there's our magnitude. Step 3, find the direction. So I'm going to go back to my diagram, locate where am I going to put this angle? Well, it's already there. Angle theta is at the tail of my resultant again. At the tail of the resultant. Okay, that's where I want theta to be. Okay, now for the angle theta, I'm going to use sine law for a triangle like this. So sine law, always write the angles on top if you're solving for the angle. So sine of theta divided by its opposite side. So its opposite side is the 5 units here in the red in my diagram. So 5 equals, you have to find another ratio that you know. And so the only other ratio that I know is the angle 150. So the sine of 150 over its opposite side, which we've calculated, which is 12.6. Okay, so you don't need the entire sine line. Or sine law has 3 ratios. You only need 2 ratios of the 3. And then you solve for theta. So sine, if I multiply both sides by 5, sine theta equals 5 times sine 150 over 12.6. And then theta would be the inverse of that. So theta is the inverse of 5 times sine 150 over 12.6. Okay, and then make sure you remember how to do this. Take some time to do this on the calculator too. Make sure you get the correct angle, which should be 11.4 degrees. Make sure your calculator is in degree mode. If you're not, if you're in radians or another one, then you might get the number wrong. If you have difficulty getting 11.4, let me know. Check that you're doing 5 times sine 150, then enter, then divide by 12.6. Okay, some calculators, if you do it all in one line, it's going to do 150 times divided by 12.6. Then take the sine of that, then multiply by 5, and you'll get an entirely different answer. So be careful. And then finally, the concluding statement. Vector R is, or the resultant is 12.6 units at 11.4 degrees relative to vector V. Okay, so here's the concluding statement where if I don't have quadrant angles, quadrant bearings, like north, south, east, west, then I'm allowed to write it like this. So resultant is 12.6 units at 11.4 degrees relative to the vector V. Okay, when I say relative to vector V, I look at my diagram. The 8-unit vector is vector V, right? So that theta is being made in reference to this vector here. So that's how I will express it. Okay, so that concluding statement is important. That's like 1 mark of the whole thing for the whole problem, if that was a test question. Okay, last example on the last page. Very easy. When you have vector expressions, you can simplify them like algebra. U plus V minus U is just U minus U is a 0 vector, and then I have 0 vector plus V, which is just vector V. Okay, so you can simplify vector expressions like algebra, like algebraic expressions. Okay, P plus Q minus P minus Q, right? That's just vector P plus vector Q. If I take out the brackets, minus vector P minus vector Q. Okay, and then P minus P is 0, Q minus Q is 0, so that the result is the 0 vector. Every other rule, like distributive property, will also apply. We'll look at that in the next section, 6.3, but it works. Okay. The focus really in this section is looking at those vector diagrams, how to draw vector diagrams. So the example with the cosine law and the example with the Pythagorean theorem, those are the problem-solving examples we're going to see over and over and over again in this chapter. For practice, there are some textbook questions I'd like you to look at. And where the textbook is lacking, I provide also a few problems down here for part A and part B. Okay, so you're going to have today and tomorrow night to work on some of these practice problems. And I'm going to stop the video here. For those watching, please like and subscribe.